Okay, so we're all ready. Great. So what I wanted to do was originally was work out how to deform contours to derive the Feynman propagator versus the time ordered, like the non-time ordered products versus the commutator and so on. But I thought that the most essential idea there is already captured in a much more simple quantum mechanics exercise, right? So that has to do with field theory, whereas with just quantum mechanics, you can already see the key feature of the path integral, which is time ordering, right? So here's something strange that you hear about the path integral. You say that, well, it's just a sum over all possible trajectories weighted with the classical action, or whatever. If you're a little bit more enlightened, you'd say there's some effective action or something. But these are still very classical notions. Right? If I give you the quantum effective action, you can just find the equations of motion, right? That's fully quantum mechanical in principle, right? But you're still dealing in classical fields, right? It's kind of confusing. You'd say, well, okay, well, what's so quantum about all of this? Well, quantum mechanics is about operators, right? Operators don't commute. That's what makes them interesting. So sort of resolving this tension is what we want to do today. So there's the basis of your understanding of the canonical, the operator formalism of quantum mechanics, you say quantum mechanics of particles, which is the canonical commutation relations. X and P commute together. They don't commute. Their lack of commutation is captured by Planck's constant times I. Whereas the path integral is just a sum over paths weighted by the exponential of the classical action, right? So let's see how you can get one from the other. So that's what we want to try to do. So this is honestly an assignment I had during my master's. This is kind of cute. It was like part of an assignment that I had. So I could lay it out as an assignment for all of us to do. So yeah, I want there to be some participation from you guys. Would be best. I feel like you get most out of this. So we'll start slow and then sort of build up to what it is we want. Okay, so first, have you all ever tried, have you all ever seen the derivation of the path integral from the operator formalism?
I think so, yeah.
Yeah, I remember going over, like I've seen it, but I do not recall it.
Okay,
Yeah.
that's fine. We can try to rederive it.
Mhm.
Um, anyway, so let's start by remembering the fact that the inner product is time independent, right? So this is a statement, and could any of you guess how you would prove this?
It's basically,
Um,
yeah.
yeah, so time evolution is just some unitary operator acting
Good.
on psi of 0 and phi of 0. So you'd have u dagger u, and that is just 1. So that
Right.
doesn't contribute.
Right. So this is u of t. Now this would be psi of 0. Am I doing this right? Yeah, phi, psi. Okay, phi. So this, oh, no, 0. So just to clarify what Sharonil means, if we had a time-independent Schrodinger equation, u would basically be a power I minus I, whatever, I, ht, or h is the Hamiltonian. If it were time-dependent, it would have a bit more of an involved form, but essentially you would still have it being a unitary operator, right? So it would be the time-ordered exponential of the integral d, so integral up to t of dt prime h of d prime, something like this. So in either case, it's a type, it's a unitary operator. And, this property of it being unitary tells us that, okay, so let me just put all of this on another line. Tells us that this product is time independent. We agree?
Yeah.
So use unitary, and for simplicity, just think about it like e power iht. Okay, so there's supposed to be an I here, but nevertheless, this is just a more involved version of e power iht when the Hamiltonian depends on time.
Question.
Yeah.
For the time ordering, right? That's not something that just exists, right? That's something we have to put in by hand.
Well, no. So, okay, let me tell you what this means. So this is actually kind of interesting. The defining property of this u is actually a differential equation. T equals h. Well, let me write it this way. Let me write it as h times u of t. It's probably an I. I think there's an I. I don't know.
Yeah.
Okay. So now this thing here, this time-ordered exponential, is the most general solution to this first-order differential equation.
Yeah.
So you can essentially derive this time ordering by trying to integrate this up step by step.
Okay.
And this is very similar to, if you recall, the notion of parallel transport in general relativity. So the parallel transport equation, so let's see. So you compare this with, so you have some parameter that runs along a curve, right?
The Christopher symbols, yeah.
Yeah, so more generally, it's just going to be the connection, right? So how do you want to denote the connection? Whatever you like. Call it A, yeah. So in Yang-Mills theory, you would have called it A. Should have A. I'll just say A dot gamma. Maybe there's an I, maybe there's not, but ultimately it doesn't matter. So in general relativity, as Pradyut said, this would be the Christoffel symbol. If we were doing Yang-Mills theory, this would be the Yang-Mills connection. But nevertheless, you have some bundle, you have a connection. And how you would solve this equation is through the path-ordered exponential of the connection integrated against this parameter.
Right. Yeah, but isn't path ordering also something we have to put in ourselves? Like that is the thing that comes from Dyson, something that Dyson did, I think, right?
No. So Dyson series is actually a representation of this time-ordered product.
Okay.
So the path ordering or time ordering comes from the iterative solution of this equation that you're deriving. Right?
Okay, I see.
When you try to solve this, when you try to write this as an integral equation instead of a differential equation, then you get this path ordering or time ordering. And in the end, as you said, the most useful thing to do when you have this time-ordered product, a time-ordered exponential, is to expand it. And then this expansion is related to the Dyson series in the interaction picture.
Okay, so the ordering is coming in from the fact that it is an iterative procedure.
Exactly. Yeah.
Okay.
Yeah. That's good. So it's good that we reminded ourselves of these facts. Any more questions? So remember, this was my assignment at some point. It's not really your assignment. You can ask how many other questions you like. Oh, sorry. Oh, fine. We can continue. So now I should tell you what this K is. K is basically your right. So K is basically another way of writing U. And there isn't much to show here. It's just that you've evolved psi with K, right? Whereas you haven't with psi star. So this is the starting point. I mean, the reason for this step is the starting point for deriving the path integral. Because what you're doing in the path integral is you're setting out an initial state and a final state,
Right.
which are at different times.
Right. And at each
Right.
iteration, you have one term coming in, right?
Exactly. So Rahul is jumping ahead a bit, but he has the right idea. So now this K, could we guess what equation it satisfies?
Some sort of Green's function, right?
Well, yeah. Well, it's simpler than that. It's
It'll be
just this
the time
equation.
evolution equation, right?
Yeah, exactly.
But wait, but isn't it going to be like a kind of like a discretized version of that? Because like you're like taking one bit and then evolving it to a certain time t1 and then evolving it to t2 again. Like when
Well,
you're going to be defining them in the integral.
right. So right now it's just one big step from the
Okay.
initial to the final. Right. So K is just propagating you. So basically you just have to recall the fact that K x f t comma xi 0 times phi, right? Xi 0 is phi t.
Won't it be
Right.
xft?
Yeah, xft essentially.
So this k is not just evolving it over time; it's evolving it over space also.
Well, there's only one. So here, all that's really happening is x. So this is kind of redundant notation because xi is just x of t equals 0, x at t equals 0. xf is just
Oh
x
yeah,
at t
fair
equals,
enough. Yeah. It's 4 vectors, right?
Right. So that's the simple thing about quantum mechanics, is all one dimensional. Now, clearly, if we're doing this in field theory, it'd be a little bit more involved, but it's just going to be a bigger version of the same exercise. But now, okay, these guys were all talking about doing this step by step. So what does that mean in terms of equations? So if I give myself these k's, what can I do?
Break them up into chunks.
Exactly. So what does that mean? So
Divide by n, I guess, and then let n go
well,
off to a big number.
well, basically, there's going to be a product, right?
Mm-hmm.
There's going to be a product of k's. So k n n 1 right product equals I to f. This is some Planck notation, and then I have phi of x I 0. So sorry, this is
that I minus 1 has to go
notation.
in the bracket.
Yeah, it has to be in the denominator, like in the subscript. So what this product is basically telling us is that we can break up the time evolution from the initial time all the way to the final time by just doing this in steps, right? So you have n steps. Now, we can give this some form, right? Before proceeding, we can try to ask, well, what does this really look like? And we could do this in terms of wave functions, but we could also do it in terms of states, right? So this inner product, okay, so what do I mean by that? So that integral expression I had, right?
Yeah.
What it basically is psi of t, right? And then I have phi of 0, right? And then I have something in between, right? So I have a product here. So K, in other words, is going to be like the matrix elements of U, right? So in other words, we can take this product in in the following way. F. And I want U T sub n. This is just for lack of better notation. Now, let me just clarify something before this gets confusing for anyone. When I said that the matrix elements so say I give myself some position eigenbasis, right? So I have xi t sub I. And remember, what this is just a bit redundant because xi is just x at t initial, which could be 0 for all you care. So this that's sort of the definition of what this k really is, right? F I sub I. Now you could ask, why am I going back to the expression in terms of the bracket notation? Well, in the bracket notation, it's easier to see tricks like insertion of identity, right? So you can resolve, okay, so let's get there. So you have a, yeah, so basically you have a product of u's here, right? So let me put the product inside just to give us the sense that this isn't just one u.
I just had a question.
Yeah,
So, well, aren't you changing your name? So, it's just a matter of labeling, but like you're going for p of 0 to psi of t. That does that mean that um like um phi is essentially different from psi? Or like do we rely back on the previous equation where you just call the initial state phi and the final state
exactly.
psi.
Yeah,
Okay.
that's really all it is. It doesn't really matter too much what
If you're
else
giving
phi
them
and
the
psi
same
are.
name or if you're giving them different name.
Yeah, so here we're just focusing on these as eigenfunctions of the Hamiltonian and like position, right? So it only really matters that phi is at x equals 0, t equals 0, and psi is at x equals
No.
t, whatever, or x equals xf and t. So now what we can do, right? So what does it mean to get this product of k's, right, in this equation from here? If I wanted to break this up,
You have
well, you just need to start inserting a lot of these, right? Because this is how you get from u to k.
so you have K1, K2, K3, so on till Kn.
Right. So basically what I want to do is I want to get matrix elements out of this equation, which is written in terms of the bracket notation. So here we'll meet a trick that's useful forever. It'll be useful forever. Okay. And this is the resolution of identity, inserting the resolution of identity. Right. So let's just take a moment to remember what that means. I want to go, no. Okay, so solution of 1. So I want to give this, put this on the next line. So what is this rule? Well, you basically say that the sum x right, it doesn't really matter. that it's X. This could have been P. This could have been
It
E.
sets up an orthogonal basis kind of thing.
Exactly. So it's a property of, it's one of the properties of your basis, right? Here we're interested in the eigenfunctions in terms of position. So we'll use X, right? So now what we're going to do is we're going to insert n of these. Right, so we're going to insert n of these sums so that we can get ourselves from u's to k's, right? So to this product of k's. And remember, all that phi is x I comma 0. And psi is xf comma tf. Sorry that I used this notation redundantly, but that's really all they are. They're the initial and final state.
I have a question here.
Yeah.
This might be just me getting kind of confused with the notation, but in the resolution of identity, when you wrote it as summation of over E, like the energy states are discrete, so that makes sense. But when you're saying you're summing over X, and I'm assuming X here is position,
There should be an integral.
Exactly.
Yeah.
Okay.
So that's sort of a generalized summation, I guess. But yeah, you're right. Here it should be an integral. And it matters that it's an integral because this is going to form the measure of the path integral.
Oh, right. You're going to get a product of dx1 to dxn.
Exactly.
That becomes your... Oh, okay. Right. Yeah.
Yeah. Very good. So is that clear to everyone? Because that's sort of an important point. So now, as Shireen said, I have a product, right? Let me drop the, actually, let's not make it too confusing. Let's just call this psi because we kept calling it psi before. So let's say this is x f f, right? X
f minus 1.
n
No,
minus
n.
1. So sorry, there's just a lot of these letters, but I hope you can follow what's going on here.
Then won't the first integral, it will be dx n minus 1, right? The last one.
Yeah, you're right. It should be n minus 1. Actually.
Oh, and there'll be one dxf too.
Yeah, so really let's call this dxf, dx n minus 1, just so that we're clear of the notation switch. Right?
Yeah.
So in between here, there was a u, right? Which became what? Which became a k. So we'll put all the k's to the right. So basically have a string of these x's doing their thing, right? So you have all the way to
x2 and the next one.
Yeah, so x2, x1. I don't know what this is.
Then we have
So this is not x1. Sorry, we call this something. We call this phi.
xi.
Phi was our xi.
Okay.
So, okay, we were calling it I. Okay, let's call it I then. Let's not get too confused. So then we'll call this I2. Okay, so this is stupid.
Oh, God.
Convention where one is I and n is f. Sorry for that. But now we have a product of these k's, right? So basically we have a product as we did before of n equals I to f, as we remember. And we have, let me just copy it from the above line, these arguments. Right? Now, okay, so now there's a few steps in between which involve the insertion of p eigenstates in the same way, like resolution of identity in terms of p, which you then use.
Exponentials.
Exactly. Then you turn those into these exponentials, and what you'll start to find is e power ip xf minus xi times. Okay, so let's actually, we could do this more slowly. Sorry, this might be, again, going fast. Now, we agree that these k's now are just the matrix elements of u's. So what were the matrix elements of u's? Matrix elements of u's was e power iht, where h is now just a function of x, right, and p. Right now, that's a weird function to write down because we only have position eigenstates, which means that any function of p will be a function of the derivative operator. So let's just keep it as k. So it's a bit of a pain to think of it in terms of, it's basically a bit of a pain to think of h solely in terms of x, because that's really the Schrodinger equation itself, right? So you're exponentiating a differential operator. It's kind of weird. You can do it. It's just weird. But first, let's make this a bit simpler. Now, position eigenbasis, right? The position eigenstates are all orthonormal, which means what? Which means that if I have
the psi and phi that we chose initially, they are position eigenstates, right?
Yes. So they're basically xf/tf and xi/ti. That's all they are.
Okay.
So you only get delta functions from them too. So what do I mean by delta functions? I mean that this is delta xa minus xb. So that's the sense in which position eigenstates are orthogonal.
You said phi would be xi?
Yeah.
Oh, then the integral won't be xi plus 1?
Oh, yeah, sorry. This is going to be xi plus 1. Where is this? Plus 1 because of our stupid notation. Yeah.
And also, I think you have to adjust it in the measure too.
Yeah.
Yeah. Fine. So now you have a product of delta functions appearing here. But the delta function is a little bit unsightly. So you can introduce a trick. Okay, so what's the trick? So this is just a property of the Fourier transform of 1 is the delta function. Is another way of saying it. This is the inverse Fourier transform. Actually, no, Fourier transform, whatever. I don't exactly remember the conventions, if it's a minus or a plus in the, but you get the idea that if you have a Fourier transform, you're going to get this delta function.
Right.
And now, okay, let me fix my notation so that they don't come back to bite me. This, I think, should be a minus. And really, let's concentrate on the case where this is all time, like the Schrodinger equation would be time independent, so that we just have exponentials to handle. Now, what is this that I've done here? Well, another way to think about this is x p. Sorry, there's this, I don't know what that is. X p p x integral dp. Yeah, and then this x is a, this x is b. Because xp is e power ipx. Px is e power minus ipx. And that gives me the two terms here that come together like this. So why I wrote it this way is just to impress upon you that I could transform each of these delta functions into exponentials by just inserting, again, resolving identity with respect to p and not just x. right? So now, say I did this everywhere in this line. What I would then have is, so product of integrals of dx.
It basically converts to the sum in the exponential.
Product of integral of dp. I won't write down the indices because we've already confused ourselves amply with that. But by now we should be clear what these things mean, right? So you have this pf to pi, xf to xi, so I plus 1, whatever. And then you have this product. So fine. Oh, we get each of these. And you have e power I n x n minus x n minus 1. Right, so I have a sum.
Yeah.
Sum over n. Now I can write my k's, right? I have a product of those k's. So in the exponential, they're all adding. Right? So I can write my k's in terms of h. Right? So I have this x of hn pn. IH t sub n. And what do I have? I still have my product of phi, so psi of t, phi star of 0, whatever. This should be in the
So just one thought I had here. So essentially, it's some sort of a game of you writing down the complete expansion of the resolution of one. Basically, you write down the complete expansion of what one is, and then you kind of like do a Fourier transform and inverse Fourier transform and kind of play around with that to resolve it into delta functions, and then write product stars exponential, so it can get converted to the sum. Okay, cool.
Yeah. So well, we could do other tricks here too. We could write this as a discretized derivative. So we put a t and then we put a t here, or let's put a k. Sorry, whatever that means. And you know, or is it n? Whatever. The point is that this is starting to look like pq dot minus h dt essentially. Right. So if you want, you could write this as, sorry, we had tn.
Oh, so that's where the legendary transform comes into play.
Exactly. Exactly. So now, what do you have to do to really do the Legendre transform? You have to do the p integrals.
Right.
And now you remember that, or let's just give ourselves a simple Hamiltonian, right? So the Hamiltonian really, classically, this is not, okay, if you want, you could write this as the operator. But in the exponential by h here, I really mean the classical function that you call the Hamiltonian, right? So it's h of p and x is like p squared. This is 2m plus u of x.
Oh, so then it's just something like completing the squares for p, and then you get a Gaussian integral or something.
Exactly.
Like a bunch of Gaussian integrals.
Exactly. So what happens is that you can do the Gaussian integrals.
But then this is assuming that my potential term is just purely position dependent.
Right. So that's also what you mostly want, or what you mostly have in mechanics, right?
Yeah, that's fair.
Yeah, no, in things that are higher power and momenta, things could be, you have other things to worry about, let's say.
So I guess just to like slightly sidetrack, do you have anything in like QFT where your potential would have like a p dependence?
Yeah, so in QFT, what you could do is you could want, like maybe you want a regulator, right?
Mhm.
So the analog of p squared in QFT would be a term like phi, is this box, square? I don't remember. Box. Phi box, come on. No, there's no box, so it's square. How do you get this? Yeah, square. So this is your usual kinetic term, right? If it says it's a free field theory. Now the thing is that even in free field theory, if you did the path integral, you would get a determinant.
Mhm.
And that determinant actually diverges. But also say you had this plus some potential, right? So you had some potential v of phi. Now maybe you wanted some clever way of regulating this theory, right? Because you'll have divergences down the line when you start to close loops, Feynman diagrams, and so on. So what you could do, that's not where I wanted you, is write this as phi times, so this is going to look a bit crazy. Lambda square.
So you
Phi.
give a potential. So this is basically perturbation, somewhat, right?
Well, right now this is just, it's a sort of complete redefinition of the action to some really crazy
Yeah,
thing.
you're kind of representing. Okay, never mind.
Wait,
Yeah, okay.
what's the
I didn't see the
square
meaning
acting
there.
on in the exponential?
It's not acting on, it's really just the exponential of the square operator, which means that you expand it in powers of lambda.
Oh, powers of lambda. Right. Okay.
So here that means, okay, so if you really expanded this, you'd have something like phi, you'd have phi box phi plus phi box squared phi over lambda squared plus so on. And you can use lambda as a regulator.
Okay.
So you give you give yourself all these whack higher derivative terms, but then you can use them to sort of regulate divergences within loops of Feynman diagrams. And then take lambda to infinity. Yeah. So sorry, there's a minus here. So there's going to be minus. Sorry, take lambda to 0. So basically you have e power minus infinity. So it goes to 0. The extra contributions after 1. So this is a really crazy way of regulating. You could think it's a really crazy way of doing the regularization, but actually it's what goes into Polchinski's exact RG equation. And sort of how Polchinski derives this exact RG equation. Uses this regulator. But usually the reason why you don't care in QFT by and large, or at least when you do perturbation theory, about higher order terms in the potential, right? So you could have u of square, right? Some polynomial function phi power n plus v of phi. It's just that this is just going to be very irrelevant. You know, just by power counting, this is always going to be really irrelevant. So under RG, it's just going to go back to, it's just going to flow back to 0. And that's also why you're allowed to add all those higher derivative terms and use them as the regulators, because they're all irrelevant from anything you could care about. Like rarely do you actually have a non-trivial fixed point that involves those higher derivative operators. But quantum corrections will generate them. Right? So in some sense, the coupling of all of those higher order, so if you have a renormalizable field theory, say you're doing phi-4 theory in 4 minus epsilon dimensions, then you generate these higher derivative operators. It's just that their couplings are all determined in terms of the phi-4 coupling and the mass. So it doesn't really matter that they're there. So you know that's sort of the upside. But yeah, you can have situations where they come into play. And so also, like if you look at general relativity, you expect quantum corrections to come in terms of higher curvature terms.
Yeah.
Right. So higher curvature terms are what? They're basically higher order derivative terms with respect to the metric.
Yeah.
right? So the Ricci scalar term is going to be a two derivative term, but then if I add something like r squared or like r power 4 or something, you start to have higher derivatives. And those are the quantum corrections that you have to account for.
Yeah, I've always wondered about those. The higher order, derivatives. Like we never addressed them, and I was like, oh, but yeah.
Yeah, no. So the
Yeah.
thing, they're kind of a pain. They could lead to all kinds of issues, instabilities, and all sorts of other things when you actually try to solve field equations with them.
Right.
But
Don't
there's some great claims to fame about getting the right coefficients for. So like the stringy corrections are always some particular
right,
numbers you get in front of these whack higher order derivative terms. But
right.
yeah,
And I'm not sure if I understand this wrong, but aren't they the cause for torsion as well coming into the theory?
I mean, I think that you could live without torsion completely, but if you wanted to introduce torsion, you could get them through some higher curvature terms. Torsion is one of those things which it takes a lot of pain to incorporate into general relativity. It's teleparallel gravity,
Right.
but you could also not do it and it'd be fine. It seems that it would be fine. And I think it's okay. You can sort of live your life without torsion. Yeah, but I'm not an expert. Maybe there's some things that become different after you account for that. Yeah. Anyway, we've already derived this now, right? So if you do these Gaussian integrals that Shire was talking about, you get an expression that looks like this, right? You have n of these x integrals. Size. Okay, sorry, I have the star on the wrong guy here. Star is not on phi, it's on psi.
Yeah.
Yeah. Okay. So you can do the Gaussian integrals and then you pick up these factors. So n is the number of steps that we have. T is the interval, the extent of the interval between initial and final time. Delta is the time step, what I was calling k. I was struggling to find the right word for it. So this isn't, let's not call this Tn, this is delta. So Tn is k times delta or n times delta, whatever it is. But you see, you get a sum of these s terms. And for a Hamiltonian that looks like this, could we guess what this is going to look like? This sum? So it's a sum over k. Oh, Rahul went out.
Oh, it's bx minus the h. Is that it?
Well, it's really going to be xk x. Sorry, am I not writing? Yeah, xk minus xk plus 1 over delta squared.
Oh, yeah.
It's like 1/2. Right, so there's going to be, sorry, this is m over 2.
Okay.
Yes, from the piece.
Sorry, this is k plus 1 and k. I did this with k minus. Okay, so this is going to be k. Yeah, plus 1, k. I think this would be k. Yeah, I think this will be k. Right? So this is going to really be, there's going to be like a delta outside. I think. It's going to be a k delta outside.
Yeah.
This is the equivalent of doing the time integral for k steps in the discretized representation. Right. So we have, this is just a discretized Lagrangian. So this k delta times, so this really goes like this. Yeah, we could do this Gaussian integrals to get this expression, but that it's just a little bit involved. It's just a little bit of algebra. But presumably you could see where this could come from. So really, if I did this correctly, it's not going to look like this. There's not going to be a Tn here. There's going to be a delta k, I guess. Now my computer's starting to slow down. Okay, it's an invalid expression. And Tn is just k times delta, right? So basically you'll have to move things around, do the integral, get the deltas in the denominator, or whatever. Reshuffle and you'll get an expression like this. So finally you could take this limit as delta goes to 0, right? Which is what you do. And then you make these time steps infinitesimally small, and then you get a derivative. You get q dot squared minus u. But this is just to impress on you, like the meaning of q dot in the path integral is really coming from this discretization. Like it's like this discretized delta thing, right?
Yeah, I can see it now. Yeah.
Sharon looks like he's still digesting this.
No. It's just I remember when I tried to learn this the first time. I read through this once and I was like, it'll be fun to try and calculate it myself.
Mm-hmm.
And then I misplaced the deltas everywhere.
It's a pain, yeah. I mean, you have to
Yeah.
be kind of careful about how you do it, and yeah, I just thought that would take a very long time, but you see where it could come from. Like you see that there's a Gaussian
Yeah,
integral.
like in principle, yes, everything is right. But whether I can replicate these calculations step by step is an entirely different issue.
You could try in your own time, and feel free to upload your answer.
Yeah. For the benefit of all. Yeah.
Yeah. But the point of all of this was just to give you, as I said, the sense of like where these steps are coming from and what this dot really means, right? In quantum mechanics, this dot is really coming from this Trotter product.
Right.
Okay. Now,
Actually, before you move on, I just want to just confirm one thing about if my intuition for this thing is right or not. So I think So if you go back up where you had the the integral dx and over dp.
yeah.
Yeah. So the exponential is px minus Hamiltonian times time. Like
Yeah.
that is like that Legendre transformation is how we define like transform between the Lagrangian and the Hamiltonian, right?
Yeah.
So
But
is that the motivation for like introducing an action there, like weighting paths of action?
essentially. Okay, that's essentially right, except there's one difference. So normally when you do the Legendre transform, P is P of t, Q is Q of t, like Q of t. Whereas here, really, Q of t is a string, QF, QI, QF minus 1, all these things up to QI, right? So this entire string becomes Q of t when you take the delta goes to 0 limit. And that's why you're getting this discretized thing, is because you're sort of treating these as
Right.
as all being sort of time independent, right? So you have a string sort of time independent positions, right? But they're all time ordered, and so both of these bits of information give you each of these functions as a function of time. That's basically the step that.
Yeah, it's basically that iterative process. Yeah.
Yeah. Now you can make your life easier. Take the delta goes to 0 limit here. Write this as integral pq dot minus h. Then do a bit more of a formal path integral, because now you're doing a path integral over paths like p of t or whatever like this. But fine, it's still some quadratic function, and then you could just do it, and then you get you get similar results. But yeah, that's the only thing that's different here. So yeah, when you go from the operator formalism to the path integral, unsurprisingly, you need to go through the phase-space path integral, because that's the only way you can sort of access this thing.
Yeah.
Great. So now, say you had any function, right? So this is just to give you the impression of what f of x means. So this is f of x of t, right? So you usually think of some functional of t, or functional of x as functional of x of t. But really, it's going to be a functional of xn all the way to x0. Right? Is this entire n-tuplet is equivalent to x of t, right? Because it's basically like saying you just take every instant.
Right.
Good. So now, say we just were concentrating at time some k time step. Can you prove this? So the equivalence between two of these matrix elements, two of these operators, is basically equivalence of the matrix elements. Right? So can we prove this this thing here?
Yeah.
This is like our Schwinger-Dyson equations from a million episodes ago.
Yeah.
Right? So you see, if you have f prime here, so let me just write this down for just...
Oh, right. It comes from
It's our
derivative.
good old-fashioned integration by parts.
I see.
Right, so now let's say that this was just a function of x k.
Right.
So it's just the derivative from each component, right? Each thing in the string.
Yeah.
Yeah, exactly. And so now if I integrate by parts, then
right,
equals minus... Okay. If you wanted to do this more slowly, you could write this as 0 minus something, 0 being a total derivative. Right, so a total xk derivative of everything. Right, so the only thing that depends on xk here is s. Right, the boundary conditions are xk independent.
Right.
We agree? Yeah. So what does that mean? It means that we can write this as, let's use curly d for that product. Right, so we take 1 over an times this product of integrals and call it curly dx. It's a functional measure. Very fancy, but that's all it really means. No. Times all of our players here. So what do we have? We have psi star of xn. We have e power is. So we have f. We have e power I mathcal s. And then we have our phi. Right? This is a 0, but then we have some other term. We have minus I over h bar. Sorry, this is is over h bar. H bar. Right, times the... Okay, so let's just copy this thing. Don't have partial xk outside. F S. Okay, it ran over the line. Sorry. So
the mathcal, right.
So mathcal dx is the product of integrals of dx over n all the way to dx1. Right? So that is the... Now this first term is 0 because it's a total derivative. Right? So this whole thing is 0. Not the integral of 0 is just 0. And this I over h bar is sitting in a weird place, notation-wise. So I'll move it. And I think, yeah, so there's a minus, and that's this expression here. So equivalence of two functionals really means the equivalence under the path integral.
Wait, I'm kind of confused.
Yeah.
How did we get from the first step to the second step? Like, what do you have to differentiate stuff
Oh,
on the
sorry.
left-hand side?
I didn't mean to copy down the left-hand side. Where is this left-hand side exactly? Okay. So this psi f psi, no, it's psi partial x
Ah, okay, yeah, that makes sense. Okay,
Okay. Sorry. Yeah, good.
yeah,
Good that you caught that.
yeah.
Are we all satisfied?
Okay. Just
Right. So we got this.
Mhm.
Now,
That looks oddly like.
like what?
Oh wait, that's the differential equation we started with.
This
Like,
thing?
yeah, that almost looks like the differential equation that we started with, right?
Oh yeah,
Like u prime
it kind
is.
of does. It kind of does, except this is a bit more involved. You see, this prime is with respect to x. Is not really a parameter. It's like it could
Ah,
be
yeah, okay, okay.
multi-component.
Mhm.
Yeah. But this is what we had many podcasts ago. This or doing the Schwinger-Dyson equation thing. Remember, we were doing these Gaussian integrals, and then this. So this was like at the heart of all of our perturbation theory. But it's just the same trick: integration by parts. So we meet it again. Now let's see what happens when f is just xk. So what is f prime?
1.
Okay.
Or no, it'll be a delta function. Well, if
No, x is just a function now.
It's not.
X is just x. It's not
okay,
x of anything.
Yeah.
Right? That's why
had
it's this step x, not x
f
of
of
t.
x. I
Right?
mean
If it was
f
x
into
of
x.
t and then we're taking a derivative with respect to x prime of
yeah.
t prime, then yeah, we'd have a delta function. But good.
Your differentiation of s with respect to x represent the force, and then your x here represent like your x is just x, so it looks like the harmonic constant. I'm just trying to understand it.
Yeah, I remember when we did this is why this discretization stuff was there's some point to it.
Mhm.
But now when delta is really small, what is this? Sorry. Okay, let's do this more slowly.
Oh, wait, when
Because
delta is really small, that's just a derivative.
right, but let's do this more slowly. Let's do this more slowly. So we have xk times
Um, sk
Oh,
times
S.
Oh, uh, this is from M
um,
mode.
That thing, right?
yeah.
Xk plus
Uh,
1 minus xk
so the
over
delta
delta.
becomes zero. Like you can
so
represent it.
okay, so
Yeah.
now first we have to decide what is pk plus 1 and pk minus 1. Right? Because what happens here is that we have xk appearing in two places.
Right.
Right.
We have one term with xk plus 1 minus xk, and then we have one term with xk minus 1.
Right.
See, this is between two pairs, right? Xk plus 1 minus
Mhm.
xk. Next term is going to be xk minus 1.
Right.
So then
Yeah.
we're going to have
Yeah,
two
like
terms,
k plus one.
right?
Yeah.
Each of those terms is going to be of the form xn minus xn minus 1 over delta, right? Times m. The
Yeah.
twos are going to cancel,
Mm-hmm. Right.
right? So what we're going to have is going to look like this. It's going to look like, if we really thought about it, it would be p k plus 1 xk minus xk p k minus 1. Because there were two, so p is just m xk minus xk. So p is mv dot, right?
Yeah.
So mx dot
And
is mv,
So,
right?
yeah,
This is our basic expression for it. But there's two of these, right? It's either the one coming from the k plus 1th derivative or the one coming from the k minus 1th derivative.
Mhm.
But now these are automatically time ordered. So they're only going to appear in certain, if it's going to appear in the path integral, then you can't have xk after pk plus 1. It has to be in this order,
right.
yeah.
and vice versa.
So this is basically the commutation relation.
That's the commutator, yeah.
Exactly.
Uh,
Exactly. So this implies that, oh shit.
Oh, wait.
Is this I or minus I? I don't know. but that, let's see.
It's IH bar.
Yeah, IH bar. Good. Now, we're talking about these XKs and PKs and all these kinds of things, and that's important. Why? Because in the canonical framework, these position and momentum operators are defined at some time,
Hmm.
right? And so that's why it's important that we're using these discretized pieces to derive the commutation relations.
Right, right.
So you see, the time ordering is what's giving you the commutation relations here. So the commutation relations are a consequence of the Schwinger-Dyson equation.
Wow. Hmm.
And that's sort of what is quantum about the path integral.
Mm.
It knows about things like time ordering.
Right.
And it's also going to be what lets us straightforwardly derive the Feynman propagator from the path integral, and maybe not the commutator, right? So that the commutator is something you do with the 2-point function. You just deform contours, so wherever you get the, okay. Or just a plain Wick function, the real 2-point function.
Yeah.
But the path integral picks a time-ordered one as a Feynman propagator. So what that means is you have to do something very weird with time if you want to get other things from the path integral. So for example, if you want to get a thermal state, you're going to have to take time to be imaginary instead of going in a circle, because it's a trace. You need trace e power minus beta e or beta h.
Oh wait, does this tie into what I spoke about last time, where like the
Yeah.
periodicity and the time thing makes it thermal?
Yeah, yeah.
Oh,
So for a second, we could dwell on that, right? So now side thermal state. Okay, so the point is the path integral always time orders, right? So if you can't mess with the time ordering, you mess with the time. Okay. So now, say I wanted to derive. Okay, so the thermal state is characterized by a density matrix. The thermal state is a mixed state. It's maximally mixed, which means it's diagonal. And it's characterized by a density matrix. And the density matrix in the energy eigenbasis is of the following form. Beta E sub n. Whoa, too much. I have to look. Okay. I always do this. So now the partition function. So let me do this. If we were just in how should I put it? In pure state, this would be 1. It's kind of pointless, right? So really, the trace of rho, which is going to be the trace of e power minus beta h, right? And here, beta is given by 1 over the Boltzmann constant times the temperature. Why is there a plus here? I don't like this. Okay.
Yeah.
Now, if you wanted to derive this from the path integral, this partition function from the path integral, guess what you do? So what you would have to do,
you have to
since
write
you
it
want,
in, don't you have to do something like complexify time or something to write it in a Euclidean form?
Exactly. So what you would do is you would essentially think of, okay, so first of all, what you normally do is you think about this. Sorry, I've done something weird here. There's a typo. Let's just break. Okay, let me break here too. So what you would do to write z now is pretend like you were really in one higher dimension. So you take a space-time view of this, right? and you associate your age to some kind of Euclidean action. But the Euclidean action can't be something that has IHT. Like, that's not what you want. You want something like minus HT.
Right.
Right? Minus HT with period beta.
Right.
So really, you do a path integral in imaginary time.
Okay.
So what you basically do is you think of this, say this is a one-dimensional system. You have a one-dimensional system along a line, and so that's one spatial dimension.
Mhm.
And you append to this Euclidean, so you append to this another space-like direction. But this is like a Wick rotated time.
Right.
And you cook up a classical statistical system on this appended direction, where the statistical model's Boltzmann weight, right? So statistical, okay, so let me define what I mean by that. So if you have a statistical model, then you have to write the classical partition function as some kind of, you can write it as some kind of path integral of some configurations. What are we calling them? I don't know. Let's say x e power minus. So you have some expression like this, right, with minuses instead of i's, right? And the point is that this thing, if you take pq dot minus h, right, with time being Euclidean, will give you the same thermal state here, with h being given by this h.
Right.
And additionally, you will need to take the periodicity to be beta.
Right.
Because what you're doing now so again, we have to write this as some Trotter product expansion, right? Like what we did before. Here, you're going, since the trace, your initial state and final state are the same thing.
Oh,
right?
all right. Yeah.
Right.
And the sort of,
So it's cyclic.
the prefactor of h is beta. So
Right.
that sets the periodicity of this direction.
Right.
But it's not an I, it's a minus, which means it's imaginary. So that's why it's a circle in imaginary time.
Got it. Okay. But
and you could do way crazier things. So if you wanted to calculate in, so normally when we talk about S matrices and things in quantum field theory, it's in out, right? Your transition amplitudes. What if I was doing field theory in de Sitter space or something where I have some in, like I'm looking at studying some inflationary model, quantum field theory on de Sitter space, and then I want to calculate some state of quantum fields defined at the surface of last scattering or the end of inflation or something. So the space-like surface.
Right.
Here I have to calculate some in correlation functions.
Why do we need in?
Well, it's just the nature of the observables that you're measuring.
Yeah.
Okay.
Right. So really what happens in inflation is that you have a period of accelerated expansion which ends at a certain time, and then this is sort of preserved in the information you get from the cosmic microwave background.
Right.
And you sort of infer that state at a single instant of time, as opposed to a transition amplitude.
Okay.
Because you didn't set up the experiment, right? You weren't there at inflation sending some stuff in, and you're not going now, and so you can't do that experiment. Okay. So there you have to use something called a Schwinger-Keldysh contour, which is really crazy. It goes all the way forward in time, all the way backward in time, and it comes back to some imaginary value. Because if you just did it with the time ordered, just with the path integral, you'll get the wrong results. You're not going to generate the right state.
Right.
You have to do all kinds of crazy things like that. So these time contours play a very important role in what observable you're calculating.
Right. Yeah, these time contours are intriguing. I still don't. I mean, I get how it comes into the calculation, but yeah, the implications, I still have to think about it.
It's really bizarre, right?
Yeah.
So this actually removed a lot of my prejudice against the way people do certain calculations in de Sitter space, quantum field theory in de Sitter space. Everybody talks about the Hartle-Hawking state, right? This is some vacuum state, and it's some unique vacuum picked out by the de Sitter symmetries, blah, blah, blah. And then you think, well, what do people do actually? Well, you start in ADS space, do some calculation there, and then you Wick rotate. You take the cosmological radius to I times itself. You do some weird Wick rotation like that.
Right.
And I was like, oh, okay, that's not very principled. What's a bit okay? It's also what made Maldacena famous in the cosmological world. Like he did some calculations of cosmological 3-point functions and
Yeah.
in perturbation theory using ADS calculations essentially and
Right.
rotating.
Right.
And everybody was like, their minds were blown by that. And I was like, oh, it's not very principled. What's the alternative? Alternative is you draw this wacky Schwinger-Keldysh contour. It's like, okay, it's fine. Just go to ADS. It's way better. So, in some sense, whenever you do perturbation theory, actually, your
Mm,
time contour is always being lifted by the interactions in some sense.
right. Right.
So if you have a strictly free field, you
Mm,
do the minimal thing you need to do, the minimal deformations to define something like a Feynman propagator or
mm,
whatever it is, causal propagator.
mm,
But then once you start to add interactions, you're going to have to tilt that thing, right?
right. Right.
And this is related to things like the sum rule representation of your, like you use this Callahan-Lehman spectral representation or something.
Mm,
You notice all of a sudden that you have some very interesting analytic behavior of things like the density of states and so on.
right.
So this is sort of the this is sort of where that story connects.
Yeah.
Like the time contour story is kind of related to the complexification of momentum story. And both of these are very interesting physical things that you learn a lot by doing this.
Yeah. Let me just make a note of this so that I can think about it later.
Yeah.
Right.
Well, I guess I'll stop screen sharing.
Yep. I'll stop the recording here then. So that was nice.
Cool, cool.